15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello there. Thanks for joining us. This is Space Nuts. It's all about astronomy and space science. I'm your host, Andrew Dunkley. It's great that you could join us again this week for another episode. Today, we're going to be talking asteroids, collisions that have been occurring on various planets, but the focus in this case has been on Mars because they've just released the results of a study into 600 million years worth of collisions, and they've found out something very interesting, which could be good to know because Mars being one of our in the same vicinity as us, and what we know about Mars could be helpful in terms of what we know about our own planet. And there's a good reason for that. And the rotation of stars has been studied, and it's been rather revealing in terms of how fast certain stars are spinning, and they're trying to understand stellar rotation, which we still don't understand. We'll also be taking questions from Ken in Maroochydore about focusing radio telescopes, and Jacob in Phoenix about rogue planets. I assume they're exoplanets, although Earth could be considered a rogue planet, I'm sure, with everything that goes on here. And much, much more. Of course, we can't do it without our good friend, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Good to see you and to be talking to you this sort of fine day.
Yes, yes. It's very overcast here, so I still haven't managed to get a decent night to take my telescope out for a bit of a look around, but I'm very patient. I'll be waiting with bated breath. But yeah, it's all good fun. Now, Fred, shall we get on to our first topic, and that is the study of asteroid collisions on Mars. Now, they're looking back over a heck of a long period of time, and they've found something interesting.
That's right. So asteroids, collisions by asteroids has been taking place throughout the whole history of the solar system, 4.57 billion years. That's how old the sun and planets are. And particularly in the early history of the solar system, that the whole place was a nightmare. There were asteroids and protoplanets and planetesimals charging about everywhere in this disk of dust and gas, which we call the protoplanetary disk. But of course, as the planets formed and settled down, that bombardment didn't just stop, and it basically tailed off because all the stuff that was there to crash into things got crashed into things and used up, although sometimes there were collisions between objects that created more asteroids. But what it means is that for a body without an atmosphere, or with a very thin atmosphere, the record of craters on the surface of that body is something that lets you provide dating for the surface itself. So the mantra is that the more craters you have on a surface, the older that surface is, that you're looking back further in time. And so you can actually see directly a comparison almost with the naked eye. Probably binoculars would help when you look at the moon. And the moon's southern highlands are very, very heavily cratered. Those craters date back to the what's called the late heavy bombardment, about 3.8 to 4 billion years ago. Whereas when you look at the greyish areas, the maria, the seas, they are much more lightly cratered because it's a much more recent surface.
Yeah.
So that's the bottom line. But what scientists have done over, I guess, recent decades, because this science of crater counting has been very much more refined. But what they've done is looked for periods when the cratering rate has got higher. And you can sort of do that by looking at the size of the craters, the typical size of the craters, because as the debris that's impacting on a surface like the Martian surface, which is what they're really concentrating on, as that debris gets cleared out through the solar system, the impacting bits and pieces get smaller and smaller. And so you tend to have, the most of the craters that you would find being created within the last few million years would be much smaller than ones that were being created billions of years ago, because the debris is smaller.
Yeah.
But what people have been looking for is, as I said, the structure in the impact rate to try and see if there were eras when there were many more impact craters than before. And in fact, that's sort of been the standard, the standard rhetoric or logic that the distribution of impact cratering over time has got spikes in it. So you've got times when there's been a much higher frequency of asteroid collisions. That's what earlier studies have suggested, and that's been, as I said, the sort of standard model of what's going on.
Yeah, it'd be logical to think that, given the history of our solar system.
That's exactly right.
I feel the but coming on.
But yes, there is a but coming on. And there is new work, new studies, actually a study published in Earth and Planetary Science Letters, which actually comes out of Curtin University here in Australia, led by Dr. Anthony Legane, I think his name is. I'm not sure how that's pronounced. I hope that's correct. He's at Curtin School of Earth and Planetary Sciences. And he and his team have basically used new algorithms to look at the distribution of craters on the planet Mars. And to cut to the chase, the bottom line is that the rate of cratering has been pretty well uniform over the past 600 million years. And that is a surprise. That's the but that you just mentioned, because people have thought that wouldn't be the case. So the reason why I guess you might expect spikes in the frequency of collisions is if you get two largish asteroids smashing into each other, then and we're talking now about principally asteroids in the main asteroid belt, which of course is right next door to Mars. If you get two asteroids that collide and smash up, what you get is a collection of much smaller objects, the debris, and that you can imagine over time, over a relatively short period of time, raining down on Mars and creating a spike in the impact crater distribution. However, the studies that have been done show, and this is a quotation actually from Anthony Legane, when big bodies smash into each other, this is what I've just said, when big bodies smash into each other, they break into pieces or debris, which is thought to have an effect on the creation of impact craters. Our study shows that it's unlikely that debris resulted in any changes to the formation of impact craters on planetary surfaces. In other words, you know, the fact that, yes, there are collisions, but that doesn't necessarily translate into more craters at a given time on Mars. And this comes about because of, as I said, a new algorithm, which apparently was created by Professor Gretchen Benedicts. I don't know where Gretchen is, but that work is what has allowed this study and allowed these new insights. Just one postscript to this, Andrew, is that, of course, we on our own planet really don't have this record of impact because of plate tectonics. The motion of the continental plates actually erases to a large extent the record of impacts on our planet. There are a few well-known impact craters, and you know, you've only to think of the Chicxulub crater that you and I have spoken about very often, which is actually under the surface of the seabed in the Gulf of Mexico.
Yeah.
But those craters, generally speaking, on Earth, they don't last very long because the tectonic plates slide over or under one another, and you actually get them rubbed out.
Yeah. So being able to look at Mars and see what's been happening with them or with it gives perhaps some insight into what we've been subject to and could continue to be subject to in the future.
Yeah, well, that's right. That's why, you know, there's so much interest on looking out for near-Earth objects. It's a kind of almost an industry now that's quietly reassuring because there's a lot of telescopes looking out for these things.
Yes, indeed. Of course, the other thing about Earth is it's covered in water and vegetation. So even if there were impact points, they'd be well hidden a lot of the time.
Yeah, although, you know, there are people have looked at tsunami records and things of that sort to deduce the past history of impact on Earth. There's been a lot of studies on Earth, but generally speaking, the surface of our planet is not a good, you know, storyteller of the impact rates on Earth, just because of plate tectonics, because it's a constantly shifting thing, and the surface is constantly being renewed. That's the bottom line.
Yeah. Well, we saw some of that renewal the other day with that massive
Absolutely. Yes, indeed, we did.
Can't remember the number this morning, but they reckon that explosion of that volcano was like 9 megatons or something.
Yes, it was something of that order. It was correct. It was big. It's actually quite interesting. It's a volcano that has been well studied by astrobiologists, and relating it to studies on Mars. I looked at this in some detail 4 or 5 years ago for a talk I was doing. The volcano is called Tonga Ha'apai, and it's unusual because it's an underwater volcano. And apparently most underwater volcanoes, when they erupt through the sea surface, they might build a cone that actually projects above the ocean surface.
Yeah.
But they tend only to last a matter of months or years. They don't last long. Whereas Tonga has actually had very long-lasting cinder cones, and it's something to do with the chemical composition of the material that came up, the magma. And the astrobiologists and planetary scientists have related that to Mars because they see similar phenomena on the surface of Mars, places where it looks as though there's been, an ocean or at least a sea with a volcano that has projected through it and actually lasted rather than getting demolished.
That's fascinating. I think Krakatoa was a similar kind of volcano.
Yes, right.
Like only a couple of years ago, the newer version of Krakatoa blew up and caused a tsunami, and a similar story. One of the other undersea volcanoes that seems to have a permanent cone is the White Island crater near New Zealand.
Yep.
Which sadly made the news for all the wrong reasons a couple of years ago as well, when tourists got caught in a sudden explosion there and many lives were lost. But they are fascinating things, volcanoes. I am captivated by them, and have been up close and personal with a few. Very dangerous thing to do. They're a very dangerous thing. And of course, Mars, the home of the biggest volcano in the solar system, Olympus Mons. It's just fascinating.
Can I add a postscript?
Sure.
Andrew, which is only related to what we've been saying because it's to do with Mars. But I've just received a news report today that you remember the subsurface lake, which was detected, thought to be detected by Mars Express. The radar signals coming back from what looked like a liquid water surface underneath the Antarctic ice on Mars. Apparently has now been debunked. There's been work done that shows that this kind of reflection comes all over the place on Mars, in regions where you could not expect to find liquid water. And the thinking is that it's actually a bright reflection coming from perhaps an iron-rich lava flow underneath the ice. That's stop press results, Andrew, and it's very disappointing.
So that means Mars doesn't have nearly as much water as we thought. Is that what you're saying?
Well, certainly not liquid water.
Right.
There is still, there's still a permafrost. Mars still is very rich in ice, but possible existence of liquid water that had everybody excited, but it looks as though that might have gone away now.
Okay. But, in what we've been discussing, it does show that studying Mars can be beneficial to Earth because we learn a lot about what happens to Mars and therefore relate it to potential happenings here on our own planet. You're listening to Space Nuts with Andrew Dunkley and Fred Watson.
Okay, we checked all 4 systems and skiing with a go.
Now, have you visited the Space Nuts website recently? It's always on the go, always something to see or do or read or become interactive with. You can obviously send us messages and questions through our interface there. You can also click on the Astronomy Daily tab, which I'm doing right now, and because of my incredible internet speed, I'll get back to you in a couple of minutes. There it is. Now, this is where you can get up-to-date stories on what's happening in the astronomical world. And they refresh multiple times a day, which is very good for people who just love astronomy and space science. One thing I never fail to mention is the Space Nuts shop. Click on the shop tab and all the Space Nuts memorabilia you could possibly hoard in your house to upset your other half, it's there. So, and some of it we've got. Yep, Fred's pointing at his shirt now with the Space Nuts logo. I've got my mug in the background and the tote bags hanging there somewhere. Yeah, there it is. It's behind my chair. But yes, plenty of things on the Space Nuts website. You can get stickers too, bubble free. I've put one on my telescope. So yeah, visit us soon, spacenutspodcast.com or spacenuts.io. Now, Fred, let's talk about the rotation of stars. As I understand it, this is actually something that's in certain aspects quite a mystery when you're talking about things like stellar rotation, but also the rate of rotation of various stars is also the subject of much, well, I won't say debate, but speculation and study. And this is ongoing, but a new study has just been published into trying to solve some of the mysteries of star rotation.
Yeah, that's right. It's something, Andrew, that we haven't spoken about very much, the rotation of stars, although it was quite a big part of some of the studies I was involved with when we did big surveys of the spectra, the rainbow spectra with that barcode of information, the spectra of 500,000 stars. Let me just start by how do you measure the rotation of a star when you can't see the disk of the star? And I'll step back one step further, if I may, because the rotation of the sun is pretty easy to measure because, of course, we see the sun as a disk.
Yes.
And it was when early astronomers noticed sunspots, which are carried across the sun's disk by the sun's rotation, that determining the rotation period of the sun fairly easy. It's actually, I think it's 27 days at the equator and much slower at the poles, more than 30 at the poles. But it's rotational velocity at the surface. And if you think of the equator, it's about 2 kilometers per second. That, the speed with which the limb of the sun is coming towards you if you were looking at its equator right at the extreme edge of the sun, 2 kilometers per second. But other stars, and especially massive stars, that number can reach hundreds of kilometers per second. So they're much more rapid rotators than the sun. The sun's a very gentle rotator. But the question is that I was about to answer myself is how do we measure the rotation of stars when you can't see the disk of the star? You can't track sunspots or star spots across it. And what you do is, as I mentioned, you use this magical machine, which we call a spectrograph or a spectrometer on a large telescope. And what the spectrograph does is gives you a spectrum of the star. We don't look at them in color, but if we did, there'd be deep red at one end and deep violet at the other. And you've got these dark features in them, which are what we call absorption lines. They're caused by the elements within the star's atmosphere actually absorbing light of a particular color, and color equates to wavelength. Now, that spectrum is affected by all kinds of things, most notably the chemical composition of the star. So you get different elements in different ratios for different kind of chemistries in the atmosphere. And that was really the first thing that the very early spectroscopists discovered when they started pointing spectrographs at stars in the 1860s. William Huggins was the great name associated with that in London. So that's one thing. You can get the temperature of the star by looking at how intense the spectrum lines are. But you can also deduce the rotation of the star. So, in fact, I've left a step out because you can tell the speed of the star as well, whether it's moving towards or away from us, by where those spectrum lines appear in the spectrum. They're shifted to the red for objects going away from us and to the blue for objects coming towards us. So you can measure that shift, and it gives you the velocity of the star along the line of sight. And it's a relative of that. If you look in detail at the shape of these spectrum lines, how deep they are, how steep-sided they are, if I can put it that way, then that allows you to measure the rotation. Because as you can imagine, if you've got a star that's rotating at hundreds of kilometers per second, one side of it's coming towards you at that speed, the other side's going away from you at that speed. So what it does is that broadens out the spectrum lines in the spectrum of the star. You can measure the amount of that broadening, and that gives you the rotation velocity. So that's a long-winded way of explaining how we measure with quite high accuracy the rotation velocities of stars. And indeed, it's something, as I said, I've been involved with. Something else I was involved with was the technique of using fiber optics to analyze the light of many stars simultaneously. And we did that with our telescopes at the Australian Astronomical Observatory, the Anglo-Australian Telescope, and the UK Schmidt Telescope. Were both equipped, in fact, they both still are equipped with machines that let you measure hundreds of stars at once. But in China, They have an instrument, a telescope. It's not actually that far from Beijing. It's about 100 kilometers away, which is called the Large Sky Area Multi-Object Fiber Spectroscopic Telescope. And that abbreviates to an acronym LAMOST. And I have a connection with LAMOST, and that's because of the work I did on building fiber optic spectroscopy systems and using them. I was very privileged to sit on a couple of the oversight committees that this telescope had back in the early 2000s. So it's something close to my heart. And okay, let's cut to the chase. Are you still there, Andrew?
I'm here. Yeah, because I read this report twice, and I'm still struggling to comprehend.
Okay, good. Well,
jokes aside, I'm finding it really just is a bit much for my brain.
Well, the easy bit is that what they've done with LAMOST is measured the properties by looking at these spectra of 40,000 massive stars.
Mm.
And so what they've been able to do is analyze the rotation of those stars. And that's something you can look at in detail in connection with the chemical composition of those stars. So this is the trick, that you've got so much data, and it's why we do these big surveys, that you can say, okay, we've got this range of rotations, and we've got this range of what we in the trade call chemical abundance. That's just the chemical mix in the atmospheres of these stars. And you can ask the question, are they related? That's what this is all about. And well, that's actually something that has got, some interesting outcomes. Now, I have to say that this is still a work in progress, Andrew, and that might be why you're struggling to get anything out of it, because there's no...
That's a good excuse.
I'll go with that. There's no gotcha thing at the end. There's a kind of semi-gotcha, but so there's nothing that says, look, this is a new result. What they're doing, they've built this huge catalogue of 40,000 massive stars, and they're with all their intimate details of each star, and they're combining the data to look at where the links are. And so one of the things that people have suspected before is that stars that have a slightly unusual chemistry, they've got, perhaps more iron than you'd expect in their spectrum or something of that sort, that they are actually, their rotation is also slower. Now, that's something one of the lead scientists on this work, I'm not sure whether I'm pronouncing this correctly. It's Sun, I think it's Wai Hia from Peking University and the National Astronomical Observatories of the Chinese Academy of Sciences, which operates LAMOST. Sun says, our study, let me put it this way. Actually, let me read a couple of things, because there's some very good comments made here. Fast rotation is ubiquitous among massive stars. Our study provides clues for understanding how the angular momentum of massive stars evolves during the majority of its lifetime. Now, what the angular momentum is the rotational energy. It's not just the speed of rotation, it's how that combines with the mass of the star to make, an energy of rotation. And we all know, because we've all read Space Warp, that angular momentum is conserved. And you know that because I bet you've done this at some time in your past, Andrew. Sat on an office chair which rotates and spun yourself around with your legs stretched out, and then brought your legs in, and your rotation speeds up.
The ballerina spin.
That's exactly it. Yes, the ballerina spin. And that's because of this thing called the conservation of angular momentum. You've got, the same angular momentum with your legs stretched out and a slow rotation as you have when your legs are tucked in and a fast rotation. Mm. And that's what this quantity is about. And so for the record, I've never done it. Oh, come on. You must have done it. Never done it. I do it every day. I've got an office chair in here.
I have got a swinging chair here right now, but I am not going to do it.
You need to be, you've got to be a bit careful. Otherwise you end up in a
sensitive equipment around
with,
I certainly don't want to put my telescope through the wall.
Exactly. It's not worth it for that. No, but it's, take it outside the door or something. Then everybody thinks you've lost it. So that's all right. Anyway, the studies are all about, this angular momentum and how the properties of these stars can be linked together. So Sun, the principal author of this work, goes on to say, that they've got this property of this catalogue of 40,000 massive stars. Such a catalogue will reform our understanding of massive star evolution. Our data challenges the idea that stars with peculiar chemical abundance are all slow rotators. That's something that's been built up over the years, that people think that, but actually they're saying this is probably not the case. And so what this is really telling you is it's likely in the end to give us real insights into how stars behave below their surface. These hot, massive stars, they've got convection regions under the surface, and that clearly is going to affect the rotation of the star. And so, if you can show how that depends on chemical composition, then it may give you an idea of the way chemical composition has changed over the history of our Milky Way galaxy, and to see how, if you compare younger and older stars, and stars of certain chemical compositions with stars of certain other chemical compositions, and look how the rotation varies. What it might mean in the future is that you've got a relatively easy diagnostic of chemistry and chemical history in a star by looking at the rotation of it. That's, I think, the end product of where this work is going. I'm kind of reading a little bit between the lines there.
Yeah.
But that would be the kind of thing that might come out of this work. So it's great stuff. And I'm thrilled that it's on a telescope that had a little bit to do with a few years ago.
Yeah. If anybody wants to read the full report, it's been published in the Astrophysical Journal, so that's where you can get a hold of it. Now, I did have a question based on something you were saying, and that was the speed of rotation of our sun, which was 2 kilometers per second. Just a hypothetical question popped in my head, and you know how much I love hypotheticals. What impact would it have on our planet if the sun were faster than 2 kilometers per second in its rotation?
Yeah, that's a really interesting question, because it relates to the type of star that it is. Our sun is effectively a dwarf star. It's not that much of a dwarf. It's certainly not a red dwarf, but it's not comparable with these really massive stars. And so the massive stars are the fast rotators. So then you'd have a star that was highly luminous. The Goldilocks zone would be a lot further out in the solar system than it is with the sun. It would have definitely had an effect. And something else that happens with these fast rotators is that they're not spherical. They're slightly fatter at the equator than they are at the poles. Actually, planets are like that too. Because of the rotation, you've got the centrifugal effect that tends to push it out. Whereas the sun, and you and I have spoken about this before, and probably because of its slow rotation, is one of the most perfectly spherical bodies known of any kind, not just in the universe, anywhere in nature. Its equatorial radius is only less than 10 kilometers different from its polar radius, and the thing's 1.3 million kilometers in diameter.
That's amazing.
Staggeringly spherical.
Yeah. You compare that to Earth. I mean, our bulge is quite
it's quite big. That's right.
Yeah. Fascinating. All right. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.